In this video, we're going to look at finding the inverse of a log function and graphing logarithmic functions. So we're going to kind of continue the whole inverse of exponential using the idea that, remember, log base b of y equals x, then b to the x equals y. So they're inverses of each other, and they can be rewritten in either way. So if you can write it as an exponential function, you can write it as a log as well, or vice versa. So they are inverse functions of each other, which means the composition, if you compose the log, and you start with the log and you compose it with the b of x, so log base b of x, it equals x. And if you do it the other reverse as well, so b to the power of log base b, they both equal x. So remember, that's how we verified that they were, in fact, inverses in the last unit when we learned about inverses. So log functions and exponential functions are inverses, so they undo them each other just like the square root undoes an x squared. They kind of go together. Logs and exponential go together as well. So, for example, if you have 10 to the log base 10 of x, remember that's log of x is really log base 10 of x, then the exponent, like these kind of cancel, and it's just equal to x. Over here, log base 5 of 125x, well, that's the same thing as log base 5 of 5 cubed, or 5 to the 3x. Then you have log base 5 of 5. This is equal to, or really it undoes itself. You just get what's left in the exponent. It's 3x. Those kind of cancel each other out. Finding the inverse functions. So remember, there's two steps for finding the inverse of a function. Step 1 was switch x and y. CH. Switch x and y. Step 2 was solve for y. So remember, in an inverse function, the inputs and outputs, or domain and range, are swapped. So step 1, switch x and y. So instead, I'm going to have x equals log base 8 of y. Then step 2 is going to be solve for y. And I'm going to rewrite as an exponent, exponential function, and that'll help me solve for y. So remember, to do that, you do the base to the power of x, or whatever it's equal to, will equal y. What's inside? So 8 to the x equals y, and that one's already solved for y then. It's supposed to be a y here. For the second one over here, first switch x and y. So I'm going to kind of put this over here. So switch x and y. So x equals the ln of y minus 3, or the natural log. And remember, the natural log has a base of e. So this is really ln base e. So I can rewrite this in exponential form as e to the x power equals y minus 3. And then finish step 2, finish solving for y by adding 3 to both sides. Now that's going to be e to the x plus 3 equals y. So those are my inverse functions for 1 and 2. So switch x and y, solve for y by starting by putting it in exponential form, and then continue to solve for y there. So we'll do a few more here. So first, I'm going to switch x and y. Let's do number 1. I'm going to number these quick so they're easier for me to refer to. Number 1, switch x and y. then rewrite in exponential form. So this is kind of written backwards than you're used to seeing it. So it's log base 9 of y equals x. Then it's 9 to the x power equals y. So I'm just doing the arrows in reverse. The base to that power equals what's inside the log. And then it's all for y. So y equals 9 to the x is the inverse of log base 9 of x. So in number 2, notice you have a 49 here, and I can rewrite log of 7, 49 as 7 squared. So I could rewrite this as log of 7, base 7 of 2x. Well, then these, eliminate each other. So really you're just left with y equals 2x. Then I can switch my x and y, so x equals 2y, and then solve for y, and I get x divided by 2 equals y. So the inverse for this one is y equals x over 2, or you could say that's 1/2 x. 1/2 x. Number 3, switching x and y, and then the base to that power equals what's inside, so y equals 1/2 to the x. For the natural log, number 4, you have to remember that it's a base of e. So first, if you want to switch the x and y, so x equals the natural log of y plus 2. Then, remembering that it's a base of e, it would be e to the x equals y plus 2. So then solving for y on both sides, you're going to have to subtract 2. So if I had e to the x equals y plus 2, to get y by itself, I have to subtract 2. Now, e to the x and 2 are not like terms, so it's going to be just e to the x subtract 2 minus 2 equals y. So this is the inverse for number 4. Number 5 is very similar, and number 6 is very similar to number 3. So I think that's all I'm going to do for those. I wanted to focus mostly on graphing here because we have learned to graph exponential functions. You can graph the logs in almost the same way. They're going to look very similar. You're going to use the inverse essentially to graph them. So since they're inverses, if you have the function f of x equals b to the x, so a growth function, then the inverse is log base b of x, and it's going to be reflected over that line y equals x. If you have a decay function, it's going to be, looks like this one over here, decaying, but it'll still be, inverse will be log base b of x, and it'll still be reflected over that line y equals x. It just looks a little different for that one. So the orange that I had covered here was, the red one's the inverse and the blue is the original. So the graph of log has the following characteristics. Remember in our exponential, our k was our asymptote and it was horizontal. In a log, you have x equals h is a vertical asymptote. And so that's kind of similar to when we graphed exponential. In exponential, we had a horizontal asymptote, and it was y equals k. Since it's the inverse, the log has a vertical asymptote, x equals h. H and k is still the shift, so hk is still the shift, and b moves the graph, moves up to the right if it's between 0 and 1, and moves down to the right. Oh, if it's greater than 1, it moves up to the right. If it's between 0 and 1, it moves down to the right. And then the domain corresponds to x greater than h, so that's similar, but over here it was the range was always corresponding to the k value, like y was greater than k. So it's similar, except for that the domain and range are input and output are switched, so it makes a difference. So how we're going to graph these is the step 1, you're going to find your shift. Then step 2, you're going to rewrite it as if you have y equals log base b of x, you're going to rewrite that as b to the y power equals x. Step 3, you're going to make a table, x, y. We're not going to do any with a's in this case, just to keep it more simple. But for your table, since you have b to the y power, you're going to pick the values -2, -1, 0, 1, 2, but you're going to pick them for y and then solve for x. So it's reversed. In graphing exponentials, we plug in x's. In graphing logs, we plug in y's because they're inverse functions, so the x and y switch. Remember that relation when we first learned about inverse and how domain and range switches, so x and y switch. So my first example over here has no shift. Notice that I have nothing with the x or at the end, so it just has a 0, 0, which means that I'm going to have an asymptote at x equals 0 because it corresponds to that h value. So I'm going to have a vertical asymptote this time at x equals 0, or remember that's going to be whatever your h value is. And I'm going to rewrite it then as 3, f of x is the same thing as y, so this is y equals log base 3 of x, and I can rewrite that as 3 to the y power equals x. Then I'm going to make myself a table. I don't have an a value, so I don't need the third column, and I'm going to plug in these values, but plugging them in for y, and then I'm going to use this to evaluate for x. So 3 to the -2, that's going to be 1 over 3 squared, or 1/9. 3 to the -1 will be 1 over 3 to the first, or 1/3. 3 to the 0 is 1. 3 to the first is 3. And 3 squared is 9. And then graphing it from my shifted point, which is just 0, 0. So over 1/9, point 1 repeating, down -2. Over 1/3, down -1, over 1 up 0, over 3 up 1, and over 9 up 2. So notice this is what it's going to look like. It's going to approach that vertical asymptote at 0 here, but it's never going to cross it. So 3 to the x power equals y. That's a growth function because b would be growing. So the growth function for that would look similar to, this. And the inverse then, the log, has been reflected over the y equals x. So the red one I drew was the growth function when base of 3, and the green is the log base 3 of x. It's the inverse of that function. So that's how that works there. So if we want to talk about domain and range, then we have domain for this one is our outputs, our x's. So if we look, remember that the domain is going to correspond to the asymptote. We're going to have all x's that are greater than 0. Our x values are all output to the right. And range is going to be all real numbers this time because we can plug in any y value we want here, any y value. We're going to have y's that from either direction. It's going to continue to grow here and approach infinity here. But it starts at 0 for the x and goes. And so the function 3 to the x equals y, that one has a domain of all real numbers and y greater than 0 for a range. But this is the inverse, so the domain and range are flipped. So it's going to be similar to what you did with graphing. That one's very similar to the last one, so I'm going to go down to do one that has a shift. So here, notice that I have an HK. This is going to be my H, and this will be my K. H always comes out as opposite, so I have 3 over 3, 3 to the right, and then up 1. So I'm going to use this as my new origin point. And now I am only concerned with the log base 4 of x. So I've already shifted it, so I can take out the -3 and +1. And now I just need to graph this. So I'm going to rewrite it in exponential form. So I'm going to have 4 to the y power equals x. So using the rewriting it, if you think about this, then my h is 3, so I'm going to have an asymptote, a vertical asymptote at x equals 3. That's this one right here that I originally drew. I'm going to have domain of x greater than 3, so everything's going to be to the right of that asymptote. And my range will be all real numbers again. So y is going to be in all real numbers, element of the real numbers. When I make my table, instead of plugging in x's, I'm plugging in y's. So plugging in y's because it's 4 to the y power equals x. So 4, I'm running out of room here. Let's see if I can shrink this down a little bit. So 4 to the negative 2 is going to be 1 over 4 squared, is 1/16. 4 to the negative 1, 1 over 4 to the first is 1/4. You can change those to decimals if you'd like, but I'm just going to approximate them when I graph it anyway. 4 to the 0 is 1, 4 to the first is 4, 4 squared is 16. I am still graphing xy points, so going over 1/16 and up and down these ones. So I am still graphing x and y points, but remember you're graphing from the shifted value right here. So over 1/16 down 2 is my first ordered pair, so I go over just a little bit and down 2. And then over 1/4 down negative 1, over to the right 1 up 0, over to the right 4 up 1, and to the right 16 up 2 is not going to fit on my graph. So I have 4 points, that's enough. I know I'm going to be continuing infinitely in both directions, but never crossing that x equals 3 asymptote there. And there's my graph in purple. So these are the key features of the graph. We got the asymptote and my table of values there. So that I used essentially the parent function is what I'm doing. So I'm going to skip, we'll do one more. Okay, so my shift is going to be at 1, 2, HK. H is always opposite, so that's to the right 1. And up 2. My asymptote, ASY, is going to correspond to my h value, which is x equals 1. My domain also corresponds to that for log functions, and then the range is always all real numbers for logs, and those are reversed. These are reversed for exponential. But since I already graphed my shift, then I can just worry about y equals log base 2 of x, which I can rewrite then as 2 to the y power is equal to x. And that's what I'm going to graph. And so I'll use my xy table since it's 2 to the y power. I'm going to be picking the same y values, the negative 2 to 2 every time, and plugging those in. So 2 to the negative 2 will be 1 over 2 squared, or 1/4. 2 to the negative 1 is 1 over 2 to the first, or 1/2. 2 to the 0 is just 1. 2 to the first is 2. 2 squared is 4. Then I am graphing these as xy ordered pairs. So when I say 1/4 negative 2, I'm going to the right 1/4 and then down negative 2. So I'm still graphing them as xy. I'm just plugging in y and solving for x. And then remember, you're graphing from your origin point or your shifted point, which is at 1, 2. So when I say that I'm going 1/4 negative 2, I'm going from the right of 1, 2, just over a little bit of a fourth, and then down negative 2. So right there, about. Then 1/2 negative 1. So over a half, down 1. Over 1, up 0. Over 2, up 1. And over 4, up 2. And then it's going to continue infinitely to the right here, and then infinitely towards negative infinity, and get infinitely close to x equals 1, but never cross. And then these are the components that you need: the asymptote, the domain, the range, and then your graph. All right, hope that was helpful. There's more examples that'll be posted on Schoology, but that's all I'm going to do for today.